So good morning. Welcome to Krishna's classroom. The last time we have said that every inner product space is a normal linear space. Then of course we have from our experience that I gave an example where you have other norms and ask the question whether it comes from an inner product or not. We have seen the example, and in which we have shown that norm does not satisfy the parallelogram law, and which is a hallmark of the inner product norm, and therefore it's not coming out of an inner product. Therefore, then of course the natural question that comes up is which norms are coming from out of an inner product. This is a difficult question. Okay, first of all, from the norm we have to cook up an inner product or something like an inner product, and then we have to essentially show that it has all the features of the inner product. We shall postpone this question later because it's a very important theorem structurally, and we will try to answer this in a later lecture. But right now we take a different route. If you recall, we have said that there exists orthonormal sets. Now, what are the advantage of having an orthonormal set? And then if we can see in a vector space V, say of dimension n, suppose there is an inner product and there is an orthonormal set. We don't know. I mean, suppose there is an orthonormal set. We assume this is orthonormal. Then, see, it is quite easy to handle the expansion in terms of an orthonormal set. Okay? Let us assume that, okay, yeah. Is an orthonormal basis, and it is quite easy to expand any function in terms of the orthonormal, or what is called a orthonormal basis. Why is it so? Suppose U is belonging to V is given by alpha 1 you know that there is a unique representation for U in terms of these vectors U1, U2, etc. Un. And then you see that Uj is equal to what is it? Alpha 1 U1 Uj orthonormality tells that Ui Uj Ui Uj equal to delta I. So we use that. So if we use that, then you get alpha j equal to. Therefore, the advantage that you have is this. that U is now sigma j equal to 1 to n U. It involves only one calculation to compute the norms. Now, you see that if this property of orthonormality was not there, then what would have happened? Okay, you would have been left with n simultaneous linear equations to be solved for computing the unknowns alpha 1, alpha 2, etc., alpha n. Okay, because what happens is, okay, for a moment let us assume that this is not orthonormal. If this is not orthonormal, but it's a basis, say, still you can compute this. This is easy to compute, and then you have now for each j equal to 1 to n, there are n linear equations, because once u is given, uj is can be computed, and then all these can be computed. So you have n simultaneous equations for finding out alpha 1, alpha 2, etc., alpha n, and then the problem of solution comes into the picture. Now I'll just give a little example which will point out this. So you take R3, usual inner product. With usual inner product. Now, see, you look at these vectors, E1 equal to now you can easily say that Ei, Ej that's very easy to compute. Now you see that if you take a vector V equal to E3. This is quite easy to calculate. These numbers, these are just dot product of V with E1, V with E2 and V with E3. On the other hand, suppose you were to take U1 to be equal to 1, 0, 1. 1, 0, 0, and then U3 equal to 0. First question is, are they linearly independent? Okay, you can see that they are in fact linearly independent, right? Now therefore these three vectors form a basis, but now how to compute V? You can use this, but what you get is, because the absence of this property, they are just some scalars that you have. Okay, therefore you get three linearly three equations which can be solved. That is because the determinant of VU1 okay. u1 and vu2. No simplification is available here. u2. And then the third equation, okay. So you have three simultaneous equations. The question now becomes, you can find out alpha 1, alpha 2, alpha 3 by solving them, but you don't have any simplicity because these are some numbers, provided this is true, that is determinant of not equal to 0, which you can show once you choose u1, u2, u3 as a basis, and this is true in fact I leave it you to prove. So that gives some advantage, computational advantage, if you have an orthonormal sequence. It's very simple to compute the coefficients. Straight away you can read it out from the equations. Okay, that's the advantage of working with orthonormal sets which form a basis. So we have seen that we have introduced the notion of complete orthonormal set. What exactly is complete orthonormal set? Orthonormal set is some u1, u2, etc. u r such that uy, uj delta I for I comma j belonging to that is clear. But what is a complete orthonormal set? A complete orthonormal set, we have characterized it. There's a nice theorem that we have proved, which says that this is complete one of the equivalent forms for j equal to equal to 0. We say it is complete provided this equal to 0 implies this, which means you cannot put in new vectors and form a new set which has u1, u2, etc., ur as a part of it and a new vector added to it, so that it will become another orthonormal set. Okay, so this is the limit of making it a or building up this orthonormal set. That's the meaning of a complete orthonormal set. Okay, so this is our definition, and we have recalled this result. Now, our question that we have encountered in the beginning was this. So these are the informations available. If V is not the zero vector space, then there exists this is the existence of an orthonormal set. We are not talking about complete orthonormal set. This is quite simple. V not equal to 0 implies there exists a U belonging to V such that U is not equal to now U divided by norm U, where norm comes from the inner product, is so in every non-trivial inner product space there exists a orthonormal set. So we upgrade this question and ask, do you have a complete orthonormal set? This is the question. So does there exist That's one question. And suppose we are able to solve that, then how many elements are there? How big is this class? Does it form a basis? We have seen one thing. If you recall that theorem that we have proved on characterization of complete orthonormal set, if you have an orthonormal set, then what you can have is this. Any vector u can be written as sigma u ui ui. If where provided u1, u2, etc., un is complete. The completeness of u1, u2, un in fact assures that every u can be written in this form. That means it the whole space is spanned by these vectors, and you know that they are linearly independent also. Okay, therefore it would form a basis. So we have already proved the essential ingredients to get the result out. Therefore, let us now write down the theorem and then write a formal proof for this. I want to make some remarks on this proof also. So we confine ourselves to the finite dimensional inner product spaces, and later on you will see that the existence of complete orthonormal set in a infinite dimensional space also, that we will consider later. But for the time being, we will confine only ourselves to finite dimensional. Let us assume that dimension of V equal to n. Okay. So what we prove is this. The theorem that we prove is the following. This is on the existence of complete orthonormal set. Then there exists a complete orthonormal set what we can prove is further is that every complete orthonormal set in V has exactly this is one problem that we encountered earlier. We also made some statements about it. That means, all right, you have completion of a given orthonormal set. But how sure are you that if you take two different orthonormal sets and complete it, they are going to have the same elements? In fact, you show that there are exactly n elements, which is that where n is the dimension of therefore this is what we call the orthogonal dimension V is the same as the linear dimension of this is the main theorem. Shows the existence of complete orthonormal sets in a finite dimensional inner product space, and this forms a basis for the space. Therefore, computationally it is very handy. Secondly, you see that the orthogonal dimension is essentially the same as the linear dimension of this. Therefore, the advantage that you have while working in an inner product space or having an inner product structure to go with our linear space structure is that you can talk about, or you can have a basis constructed for the space which is orthonormal, where all your computations become simple. Now this is something which we didn't have while we were working on linear spaces in the absence of such structures. Okay. Okay, this is quite simple to prove. So we give two proofs for this. One proof is a qualitative proof, or okay, I want to make another remark. Another remark is that there are several complete orthonormal sets that you can have in a vector space. As you already know, that every vector space has several, non-trivial vector space has several bases. Okay. Now what we assert is that every every inner product space has several complete orthonormal sets in it, and each of them would be a basis through which you can make the computations simple. Now you have seen that this is an advantage. We have turned this multiplicity of the multiplicity of the basis that you can have in a vector space to an advantage. Recall when we constructed the matrix representations, etc., we said that we can possibly construct a very convenient or handy matrix representation by choosing an appropriate basis. And similar things that you can do is much simpler here, okay, because you have an additional structure, therefore it gives you more working room, or more nice things would follow in this case, as we shall see soon when we deal with what are called linear transformations. So let us give a proof of this theorem. The proof of this theorem, we have already proved bulk of it in our characterization theorem. Okay, so we'll just recall the right ingredients from there and then put them together and take the proof out. Okay, proof. Now you see, if it is not already a complete orthonormal set, then you can enhance it. How do you do that? Okay, the set is that there exists u not equal to 0 in V, and u divided by norm u is an orthonormal set. Now suppose it is not complete. Then what does our theorem say? Our theorem says that then there exists V, okay, then there exists such that equal to 0. Then choose and them together. This is again an orthonormal set. Again, you ask the same question, is it complete or not? If it is not complete, you go to the next step. Okay, then there exists a W with the property that inner product of U with W is 0, inner product of V with W is 0. Then you adjoin to this U by norm U, V by norm V, W by norm W. Okay, and that collection is a orthonormal set. So systematically you can build a orthonormal set. Now let us see. So let us make an induction argument. Okay. Suppose we build an induction argument now. Okay. Suppose we have found U1, U2, UR then there are two possibilities. Either it is complete or if it is not complete. If it is not complete, you can enhance it. Either it is complete if it is complete, then it is done, or it is not. If it is not, we know that there exists and U is so this is orthonormal. So this is the tactics that you use. Now, how far you can go? You see that now note that every orthonormal set is a linearly independent hence number of elements in any orthonormal set is at most n, which is equal to dimension of V. So you see that in a finite number of steps you can arrive at a complete orthonormal set. A finite number of steps Okay. Now what we want to assert is that this forms a basis. Okay. Now you see the span of is equal to V if and only if complete. So once you get a complete orthonormal set, then you are going to have those sets, hence every complete V. Therefore, this implies since these vectors are independent, the number of elements any complete orthonormal is N, because they form a linearly independent set. They also span the whole space. What does it mean? It means it's a basis. Okay, that is because a complete orthonormal set is a basis for the space. Okay. Is hence an orthonormal basis. So there exists orthonormal basis, and every orthonormal basis has exactly n elements, which is the dimension of the vector space. Okay, so this is what you get. So we defined earlier what is called the orthogonal dimension. Orthogonal dimension is the largest, is the number of elements in the largest orthonormal collection in the vector space. Okay, so every complete orthonormal, sorry, I think the completeness has to be there. Every complete orthonormal set in V has the same number of elements. Therefore, the orthogonal dimension, from the definition, orthogonal dimension follows that. Okay, so this is a qualitative proof in the sense that you are not a non-constructive proof. You are not actually constructing an orthonormal basis. Okay, or at best you have to keep working step by step and then construct an orthonormal basis. But a interesting proof was put forward, which is more constructive, by constructing an orthonormal basis from a given basis. Remark. we do is we want to be more constructive. Okay, so we introduce a technique called the Gram-Schmidt process. Of construction of an orthonormal basis This is what we want to discuss now. How to construct an orthonormal basis from a given basis. If it is done, and if it is done as we desire, namely that the orthonormal basis is intimately connected, I will make this clear, intimately connected to the basis that we start with. Okay? Then it is clear what we you will see the advantage of this. This is a very constructive proof. So let us prove this. Okay. Before that, it may be worthwhile to examine a construction so that you get a feeling for this. Then it is very simple. Just writing 3-4 lines, you will get the let's consider two problems. So we'll start with some examples. Work in the simplest of the spaces. Let us take R2. So V equal to R2, dimension of V over R, obviously. Consider the vectors one 0 and 1 1 1. Then this forms basis. Okay, let us draw some diagram. Maybe worthwhile to draw some diagram. It's very interesting to see what this looks like. So in R2, with some scales and so on, now you see this is O, this is the point 1 0, and we have 1 1. 1 1 is this vector. So the two vectors that you consider are 1 0 and 1 1. And you can form a coordinate axis with the scalar multiples of these vectors, and with respect to that coordinate you can go for the representations of the vector. So how do you construct a orthonormal basis from this? Now you see that okay, 1 to 1 inner product with p equal to 1, which is not equal to 0. So they are not orthogonal. So how to construct an orthonormal basis from this? Okay, so what one does is this. Okay, we want to do it in the following way, right? Start with 1, 0. Say u1 equal to 1, 0. Then norm u1 equal to 1. That is u1 inner product with u1 is 1. Now what one does is you are given u2. Okay. Right? So what we do is we take a vector which is in the span of 1, 0 and 1, 1. Okay? Right? So let now what we want is this vector to be orthogonal to 1, 0. Okay? So you write V, the inner product. This is equal to 0. So we are making it orthogonal to chosen orthogonal to 1, 0. How does that come? So let us compute this. So you see that this is V is equal to C1 plus C2 and C2. So you want C1 plus C2 inner product with equal to 0. What does it give? It gives C1 plus equal to 0. So what we need is that C1 should be C2 should be equal to minus C1. Therefore what you have, so V is equal to C1 so this is equal to actually 2C1 C1. No, I think there is something wrong. C2. Yeah. C1 plus C2 is, this is equal to 0, C1. 0 minus C1. Okay, now you choose C1 such that is normalization. So what do you get? You get mod C1 okay, mod C1 equal to 1, which means either you can choose C1 as 1 or C1 as minus 1. Both the choices are there. Okay. Right. So you have two vectors possibly. One is 0, 1 and or both are orthogonal to okay, so what you have is that the orthonormal set that you have constructed is 1, 0, 1 or 1, 0, both are orthonormal sets, and that's also complete because they are linearly independent. Therefore, this is how you normally construct it. Okay, what is that you have done? You have constructed a linear combination of 1, 0 and 1, 1. Okay, so you see that the vector V okay, so we have chosen a vector V which is in the span of 1, 0 and 1, 1. So it can be any vector with the choice of C1 and C2, it can be any vector, but we choose it in such a way that this linear combination is either this or this one. Okay, it is either this one or this one. Both are orthogonal to this one. And you see that every vector can be written as linear combination of 1, 0 and 0. Now, how do we normally process this? Okay, So the method of processing the whole problem is contained in this particular example. Okay. So what one does is you keep building up the orthonormal basis from the given basis. Okay. Step by step. One step after other. Every time you go forward one step. That means you start with a U1. U1 spans a vector space. Now you choose U2 and then take a linear combination. So you are in the linear space of U1 and U2. So the vector that you are going to construct is certainly in a span of U1, U2. So the procedure is this. Start with V1. Okay, U1. Suppose it's a basis for V. So you start with U1. Okay. Then adjoin to that a linear combination of U1 and U2. Okay, you take a vector, something of the form C1 U1 plus, what can you say this spans the same space spanned by U1 and U2. Okay. Then what do you do? You get this. So call this, say, let us designate this as V1, V2. So V1, V2 spans the same space spanned by U1 and U2. Now take U3 and write U3, go for a linear combination of V1, V2 and U3 and make that orthogonal to V1, V2. Okay, right? Make that orthogonal to both V1 and V2 and choose the scalars accordingly. So you end up with, see, V1, V2, span of V1, V2 is the same as span of from there you construct V1, V2, V3. V1, V2, V3 is constructed by taking a linear combination of V1, V2 and U3. Okay? And you know that in turn, the span of V1, V2, V3 will be essentially the same as span of U1, U2, U3 and so on. So you keep building it up in this way so that each stage you are confining yourself to the subspaces spanned by U1, subspaces spanned by U1, U2, subspace spanned by U1, U2, U3 and so on, and constructing orthonormal basis for these each of these subspaces and then put them together to get the orthonormal basis. Okay, this is the art of building up the orthonormal basis. Okay. So this is what is done in the case of the Gram-Schmidt process. So let us explore this now. Take an example. Let us take P2. All polynomials with real coefficients with inner product defined by because we are taking real coefficients, I am not putting the complex conjugation there. Now let us consider this. First of all, you observe that 1t square is a basis for P2R. You know P2R is 3-dimensional and this is the case. Now you see that this is, of course, start with 1. So V1 take as 1. Okay, you know that norm of V1 is equal to it's a orthonormal set. Okay. Now choose V2 to be a linear combination of 1 and t. So C1 plus C2t. So this belongs to the span of okay. Now make this orthogonal to V1 and then normalize it. That's the art. So what one does is this. Okay, so you make this one set C1, C2 such that inner product of is equal to 0. So that means integral 0 to 1 C1 0, that is C1 C2 equal to 0. Oh, it is t square by 2, so C2 by 2 equal to 0. Okay. Therefore, C2 equal to C minus 2C. Okay. Then take this a linear combination of these two. Okay. So what do you get? Okay. So the vector that you have to choose. So V2. Okay. So you choose U2. We have to fix this constant U2 to be equal to C1 minus minus 2. Now choose C1 such that norm of U2 equal to 1. What does it give? It gives C1 square equal to 1. So what do you get? You get C1 square into 1 4 divided by 2 2t 4t square. So 4t square t square by so t cube by 3 4 by 3. So determine C2. So you can actually compute it and decide on divide or this. Now what is the next stage? Okay, determine there are two choices possible. Okay, the plus square root and the minus square root possible. See, using this equation. Then after that, what you do? Go to the next stage. So you have got V1 V2. Now what is the next stage? The next stage is determine okay. Is orthogonal. By taking C1 V1 plus C2 V2 plus C3 T square, that is V3. Okay, then you make U3 such that U3 is orthogonal to V1 V2, and then the norm of U3 is equal to 1. Now this is the procedure. So I don't want to do this. Leave the computation to you. I don't want to spend time actually calculating the coefficients and so on. It is not difficult. Okay, so let us now run this procedure. Okay, run this scheme. You get what is called the Gram-Schmidt process. So what you are doing possibly is this. Suppose you have a 3-dimensional space. suppose you have a three-dimensional space, okay, and then you denote this as U1, this as U2, this as U3. Three vectors, three linearly independent vectors are given. Let me make a bigger picture that may be nice, more revealing. So we take three linearly independent vectors. So you have three vectors, U1, third vector, second vector U2, and the third vector U3. What do we do? The first step is normalize U1. First step is normalize . What does it mean? Take a scalar multiple of that and choose the scalar in such a way that the scalar multiple has norm equal to 1. Call it V1. So you see that U1 and V1 span the same space. Now what you do is you go to the plane spanned by U1 and U2. So this is the span of, or I will write it this way, the span of this. So you take a linear combination here. Take a linear combination in such a way that you get V2. So span of zero and norm of V2 equal to 1. That's the next. What is the third stage? Because U3 is not in now what do you do? Get V3 in the span of U3. That means you are choosing a vector, a linear combination of this. Okay? So it can be any vector in that space spanned by that. And such that now you see that U1, U2, U3 is the span of U1, U2, U3 is the same as span of V1, V2, V3. So they span the same space. But V1, V2, V3 is orthonormal. This is how one gets doing it. Okay. So you start with a sort of V3 in this direction, so that this angle is this. Then what you have, you take a combination of, so this is V1, this is V2, then this is V3. So that V1 is orthogonal to this, V3 is orthogonal to V2. This is how one works on this. Okay, let us now do the actual Gram-Schmidt process. V is assumed to be n-dimensional, any basis. So write V1, you write as U1 divided by norm of U. They are not zero, so you can very easily write define suppose has been constructed such that Vj is a linear combination of combination of now what you do is you write how to enhance this class. That's the question. Okay. Write W to be equal to UR plus 1 minus This you know is again a vector in the linear span of u1, u2, etc. ur. Okay? Then choose. Such that R, and this, let us compute this. So this is W Vj equal to sigma which, if you expand, inner product of Vj with Vj is equal to 1 because it's an orthonormal set. Therefore, this is equal to ur plus 1 Vj minus alpha j. This is true for every j, that is j. So what does one get? So you see that choose then W is now W is not equal to 0, since is linearly independent, and coefficient of ur plus 1 is not equal to 0. In the expression for W, Okay. In the expression for W, is not 0. This is more precisely, it is equal to 1. Therefore, right is 1. Zero. Now you write VR plus 5, you define as W. And the span of linearly independent and the span of equal to span of continue this argument. So, yes. You reach UN. Therefore, you get, then we have an orthonormal set linearly independent and hence a basis for that completes the proof. Okay, so let me just look at this. What is happening here? Look at this expression that you are getting. So you have got so you take this is V1. Okay. So what do? You are actually taking the projection of U2 on this line. What is that? And this vector is essentially what is it? V1. U2 V1 V1. It is a projection of U2 on U1 or U2 on V1. Okay? Take the difference. When you take the difference, this is what you need. You complete the parallelogram with this as this. So this becomes what you call U2 minus U2 V1. So this is your vector. Okay. Then what you do is you normalize it. So this is V2, which is equal to. Okay, so having constructed V1 and V2, now this is how you systematically construct it. Each time you have a vector here, what you do is you try to make it orthogonal to U1 by taking a linear combination of these two. That is, you project it here, subtract from V2 from U2, so you get a vector here which is orthogonal to V1, and then normalize it. That's all. This is it. So that's the correct procedure. Okay, so you get systematically you build orthogonal vectors, and until you get a span of this. I think that is the complete orthonormal basis constructed out of a basis. So what does it say? It says that from every basis you can construct a complete orthonormal basis. Okay. Such that at each stage, see, V1, V2, VR span, the span of V1, V2, VR is the same as the span of U1, U2, UR. That's the beauty. Okay. So step by step you are building the whole space basis, and you get an orthonormal basis. So this shows that there exists a orthonormal basis, and it actually tells you how to construct it, and it's a very handy procedure to construct an orthonormal basis from a given basis. It's a constructive proof of the result that there exists a complete orthonormal basis. Okay, thank you very much.